Okay, we're back again. We have this equation in standard form. We left off by drawing the fundamental rectangle, and then we also were able to observe that it's going to be a left-right opening one since the quadratic terms in x are the leading term being positive here. So it's a left-right opening hyperbola. So if you took any time during the changing segments, what you would want on your own is what you should have done is probably drawn your diagonals through here, through the rectangle. And those are called your what? Your oblique asymptotes, or asymptotes associated with this hyperbola. And we have a positive sloped one, and we have a negative sloped one. Negative slope, positive sloped one passing through the center of the rectangle. Now, since it's a left-right opening one, what you also should observe is that your transverse axis is right here. Transverse axis is right there. The equation of it is y equals -2. Y equals -2. Your branches then are going to be wide sweeping, it looks like, wide sweeping, and I'm not even going to draw them yet. All I know at this point is they're going to do this, something like this. Why don't I want to draw that completely yet? Because there's a couple interesting features here that we probably want to pin down and be pretty accurate with. It looks like we're going to get an x-intercept right in here somewhere, and we're probably going to get a y-intercept up in here somewhere. So we might as well do those calculations in a few minutes and actually plot those points in here fairly accurately, and then we could get a nice picture of that branch. Similarly, there'll be another y-intercept down here. And then there's a right opening branch that's out over here that's going to sweep up with an x-intercept, and that's it. And then it's going to head up towards this upper asymptote, and then the branch is also going to sweep down there. Okay, why don't we pin down the focus locations? Remember what I said previously. All you have to do, let me point out this. On this rectangle, come over here, notice that we have a distance, a horizontal distance. It's right back here in our equation, distance of 2 to the left and right of the center. And we have a distance from the center up to the top of the rectangle of, you can see it right there, 4. So we have a distance of 2 and 4. Now, that diagonal right through there, that diagonal right there happens to have a length equal to the Pythagorean relationship here. 2 squared plus 4 squared is 4 plus 16 is 20. So that distance is square root of 20. Square root of 20. You can see it right here. 16 plus 4 is 20. Square root of 20 is the distance that you're going to grab, that distance, square root of 20. You're going to grab that and lay it on the transverse axis from the center, in this case both to the left and to the right, and that's going to tell you where your focus is. So square root of 20 is a little bigger than 4, and so it's going to be -1. Let's see, we were 3 to the right, I believe, on our center, and then so we're going to come back a little more than 4 to the left of the center, and so it's going to be right over in here is where this focus point's going to be. And so that focus is going to be located at 3 minus square root of 20, comma, -2. Similarly, over here, at a distance of a little more than 4, so you don't even need your calculator on this. My scaling was 1, 2, 3, I'm sorry, let's see. 1, 2, 3, 4, 5, 6, a little more than 6, 3, and I'm sorry, a little more than 4, so it's a little more than 7 out there. So 3, I'm going to write that one down. Sorry for being cluttered here. 3 plus square root of 20, comma, -2. I hope you can read that. Very messy. 3 here's 3 to the right, plus square root of 20 gets us out there, and then we're down -2. So that's the other focus location. So it's pretty easy. By looking at your rectangle, you can see it in the geometry here. It's this diagonal length here by your Pythagorean relationship, and then you just have to lay that on your transverse axis to the left and right of the center in this case. Okay, so that nails the focus points. Now, how about the equations of your asymptotes? Let's come back over here onto this board, and I'll just, in the interest of reducing some clutter, we have a point, we have a rectangle that is looking something like this. Trying to just reduce a little bit of the clutter. And so we have this point 3, -2. And then we had a distance of 2 and 4. To get that asymptote. And let me double check that. 4 above and below the center, 2 to the left and right of the center to help us with the rectangle. And then, of course, we have the other asymptote here. Now, something you should remember from your basic algebra background is your point slope. So if we use the point 3, -2, and a slope of 4/2, which is slope of 2 for one of the asymptotes, and we also could use the point 3, -2, and the slope of the negative sloped asymptote, which is the slope of -2, we can work up the equations of the asymptotes. So recall y minus y1 equals m times x minus x1 from your algebra background. So this might be a pretty nice way for you to tackle finding those asymptotes. So y minus, be careful here, y minus a -2 becomes +2 equals your slope of 2, x minus your 3. And you tidy this up. Y plus 2 equals 2x minus 6. Y equals 2x minus 8. Now, I don't believe my math until I come back and look at my picture. So what I'm going to do is I'm going to come back here and look at this picture and see if this equation fits what appears to be on this picture here. So notice my rectangle is 3 to the right down 2, so the bottom of the rectangle is 4 below that. So this point right here is at 3, -4 below that is -6. So I'm anticipating a y-intercept down with a slope of 2. And where's the corner of this rectangle, folks? Wouldn't it be 2 to the left of this point? 1, -6. And what's the slope of this line? A slope of 2. So I would anticipate if I ran over 1, I better drop 2, and that drops in right at -8. So I can check myself from the picture here to see that that equation is correct. Picture is worth 1,000 words. It's actually worth many lines of algebra because you can gain insight into the correctness of your work. Let's do the other one real quickly. Y plus 2 again, -2 slope this time, x minus 3, clean it up. We get y plus 2 equals minus 2x plus 6, move the 2 over through subtraction, and we get minus 2x plus 4 for the other asymptote. Similarly, this point right up here should be 0, 4. You can check that using the geometry ideas that I talked about a few minutes ago. Okay, got both asymptotes. Next step, let's look at the intercepts associated with this picture. Now, remember, we have a branch heading up, sweeping to the left, and we have a right-hand branch sweeping towards those asymptotes. And so what I want to find is these intercepts, where these branches hit the axes. So that's not too hard to do. Let me erase one of our asymptote equations so I have some room. Let's come back and look at our equation, which was x minus 3 squared over 2 squared minus y plus 2 squared over 4 squared equals 1. Let's see. Why don't we let x equals 0 first? If we let x equals, here's our x, if we let x equals 0, we're going to be talking about the y-intercepts of this graph. So let x equal 0, and we're looking for y-intercepts. If we do that, letting x equal 0 here, we get 9/4 minus y plus 2 squared over 16 equals 1. This is a simple quadratic equation that's fractional. The best way to clean up fractional equations is find the common denominator of all your fractions. In this case, it's 16. Multiply both sides by 16. So multiplying both sides by 16, we end up, be careful, 4 goes into 16 4 times. 4 times 9, 36. Subtract off, 16 divided by 16 is 1. That leaves this binomial square right there, and that's equal to 16 on the right. If I imagine moving the y plus 2 to the other side through addition, it becomes positive. And I bring the 16 back over, and I'm left, I believe, with 20. 16 taken away from 36. And then we square root both sides, the square root property. And so we get y plus 2 equals plus or minus square root of 20. And so the y values then are going to be equal to 2 plus or minus square root of 20. So our transverse axis comes through right here at -2. Our transverse axis on that symmetry line. And so notice, oh, I think I have an error. Do you see how the picture helped me catch a mistake over here? Look at that. This says go up to y equals plus 2 and add and subtract above and below it. Something's wrong there. The picture catches the error. Picture catches the error. That should be a -2 and above and below to find where these branches hit symmetrically. So look right here in the algebra. If I should have subtracted 2 from both sides right here, and that would leave a -2 plus or minus radical 20. So -2. Nice example of how the picture catches an error. Okay, so then notice we're at -2, and we're going to add and subtract square root of 20 to this y reading. The square root of 20 is a little bigger than 4. So we're going to come up 1, 2, 3, 4. Actually, yep, a little more than that. And so that's where an intercept is going to be. So we're going to have one branch sweeping up here like this towards this asymptote, and we're going to have square root of 20 below, -2, down in here, and so it's going to sweep down like this. And so there's those two y-intercepts, one of them at 0, -2 plus square root of 20, and the other one down here at -2, 0, -2 minus square root of 20. Right there. Okay. I think we could find the x-intercepts. And I think we have time to just quickly do that. The x-intercepts, and it looks like there should be a couple of them from the picture. And we're going to do that by setting y equal to 0. So we come into our original equation, and we're going to let y become 0 now. And so our equation is going to be x minus 3 squared over 4 minus, putting a 0 in for y, we get 4 over 16 equals 1. This reduces to 1/4. So we have x minus 3 squared over 4 minus 1/4 equals 1, multiplying both sides by 4. And we're going to get x minus 3 squared minus 1 equals 4. So x minus 3 squared equals 5. Square root both sides, take the square, extract the roots on both sides. X minus 3 equals plus or minus square root of 5. So x equals 3 plus or minus square root of 5. So by letting y equal 0, we have these two x-intercepts. 3 plus square root of 5, comma 0, and 3 subtracting square root of 5, comma 0. So we get those 2 points. Come back to the picture to check yourself. 3 plus square root of 5. Now square root of 5 is a little more than 2, so it's going to be right out here about where I had this marked. 3 plus square root of 5, comma 0, right there. 3 is here, plus square root of 5 is a little more than 2, and that's going to lay in right there. And we should have another one at 3 take away square root of 5, right here at that location. 3 take away square root of 5, comma 0. Okay, I want to take just a moment to briefly mention the applications associated with hyperbolas, and I can do that pretty nicely since our textbook addresses this pretty well. I'll show you one problem here in the book. And I'm going to back this out a little so we can see this. And I think this will show up reasonably well here. Is that readable? Or should I be a little larger? Okay, a little bit larger, okay. How's that? Okay. One thing I didn't have time to mention earlier, I forgot to mention, is that what a hyperbola is in its formal definition is it's where the difference between the distances from a point on the curve to two fixed points, the difference in those distances remains constant. So, example here, here's your two focus points. This distance minus this distance has to remain constant. So if I was at a point here, the distance from here to the point on the curve minus the distance to this other focus, that would be the same as that difference was here. This is very useful in timing issues and sometimes in locating certain points and that type of thing. Here's a very nice problem that what you could do is pause this and read it, and it's a pretty nice discussion about how you can actually determine where a lightning strike may have occurred if you had 2 points of reference and you were able to both see the lightning at the same instant and that you knew the speed of sound. So that's one simple illustration. There are some other really useful ones related to astronomy with telescopes and that type of thing, and I want to just draw your attention to something that the authors have included in this book as well. And you may want to go to this website to actually investigate this. Hyperbolic mirrors. If you're interested in telescopes or astronomy at all, you might see if you can find enchantedlearning.com as a website. And here's a nice problem associated with a hyperbolic mirror. One final comment is nuclear cooling towers are in the shape of a three-dimensional hyperbolas where you have rotated the hyperbolic shape around the conjugate axis. Now remember, the conjugate axis is that axis that's perpendicular to the transverse axis. And so if you've ever seen one of those nuclear power plant cooling towers, they're in the shape of a hyperboloid, it's called, where you've rotated the hyperbolic shape around the conjugate axis. The reason for that particular shape is because it creates a really efficient type of ventilation or circulation of the air that moves up through those cooling towers. Okay, so with that in mind, we'll go ahead and close this session, and we hope this has been helpful to you. Thank you.